You're handed a system of 3 equations in 4 unknowns. More unknowns than equations, so there should be tons of solutions. But not necessarily, sometimes there are none at all. Before you ever pick up a pencil to solve a system, ax equals b, one condition decides whether a solution exists. It comes down to a single test on the vector b. Let's find that test. To answer this, think about what ax equals b really asks. The product ax is a linear combination of a's columns. We can write it as x1 times a1 plus x2 times a2, and so on, up to xn times an set equal to b. As x varies over all possible vectors, ax traces out every combination of those columns. That collection of all outputs is the column space of A, the set of all reachable B vectors. In 3 dimensions, if A has 2 independent columns, the column space is a plane through the origin. The 2 column vectors lie in and define that plane. Now the question becomes, does B lie in that plane? If B lands on the column space, then some combination of the columns reaches it, and the system is solvable. But if B falls off the column space, no combination can reach it, and there is no solution. So solvability of ax equals b is exactly the same as asking whether b is a member of the column space of A. Here's our example. Consider a 3x4 matrix A with rows 1, 2, 2, 2, then 2, 4, 6, 8, then 3, 6, 8, 10. Now notice something important. Row 1 plus row 2 equals row 3. Let's verify this element by element. 1 plus 2 is 3, 2 plus 4 is 6, 2 plus 6 is 8, and the 2 plus 8 is 10. Every entry checks out. And this row dependency tells us that A's rows are not independent because the output is constrained by this relationship. Not every vector B in R3 will be reachable. In other words, the system ax equals b will not have a solution for every b. To find what b must satisfy, we form the augmented matrix, glue b onto the right side of A. The right column has symbolic entries b1, b2, b3. Now we perform row reduction. Step 1, replace row 2 with row 2 minus 2 times row 1. Row 2 becomes 0, 0, 2, 4 on the left side, and b2 minus 2, b1 on the right side. Step 2, replace row 3 with row 3 minus 3 times row 1. Row 3 becomes 0, 0, 2, 4 on the left, and b3 minus 3, b1 on the right. Now for the final step, replace row 3 with row 3 minus row 2. The left side of row 3 becomes all zeros. On the right side, we get b3 minus 3, b1 minus the quantity b2 minus 2, b1. Let's expand that. b3 minus 3, b1 minus b2 plus 2, b1, which simplifies to b3 minus b1 minus b2. So the last row reads 0 equals b3 minus b1 minus b2. Whether that equation holds is entirely up to B. It's the solvability condition. So here is the solvability condition. B1 plus B2 must equal B3. Notice where this comes from. The rows of A satisfy a specific relationship. Row 1 plus row 2 equals row 3. Let's verify. 1, 2, 2, 2 plus 2, 4, 6, 8 gives us 3, 6, 8, 10, which is exactly row 3. That exact same relationship must hold for B. Right? B1 plus B2 must equal B3. This is the key insight, and it generalizes beautifully. Whatever combination of rows of A produces the 0 row, that same combination applied to B must give 0. In general, if C1 times row Y plus C2 times row J plus and so on equals the 0 row, then C1 times Bi plus C2 times Bj plus and so on must equal 0. The rows carry a constraint and B must obey it. If B respects the relationship, the system has a solution. If B violates it, no solution exists, no matter how many unknowns you have. Let's test this condition with actual numbers. First, take B equals 1, 5, 6. Check the condition. 1 plus 5 equals 6, which matches B3. the condition is satisfied. The last row of elimination gives 0, 0, 0, 0 on the left side and 6 minus 1 minus 5, which is 0 on the right side. There is no contradiction, so a solution exists. This last row is simply a redundant equation. Now try b equals 1, 5, 7. Here 1 plus 5 is 6, not 7. The condition fails. The last row gives 0, 0, 0, 0 on the left, and 7 minus 1 minus 5, which is 1, on the right. That says 0 equals 1, right? A contradiction. Therefore, no solution exists. A common mistake: seeing a 0 row during elimination and immediately concluding that there's no solution. That's not right. A 0 row on the left side of the augmented matrix only creates a problem when the right-hand entry is non-zero. Let's think about this carefully with a flowchart. Suppose elimination produces a 0 row on the left side of the augmented matrix A bar B. Now we ask, is the right-hand entry also 0? If yes, then you have a redundant equation. 0 equals 0 is always true. No problem at all. Right? The system may still be solvable. But if no, the right-hand entry is not 0, then you get 0 equals some non-zero number. That's a contradiction, and the system has no solution. One more important point: having more unknowns than equations does not guarantee solvability. Row dependencies can still create conditions on B that B might fail to satisfy. Now let's step back and see the big picture. Solvability of AX equals B isn't about the size of the matrix, it's about structure. The column space of A defines the universe of all reachable B vectors. In other words, the system AX equals B has a solution if and only if B lies in the column space of A. Elimination is the practical tool we use to test whether a specific B belongs to that column space. When we form the augmented matrix A bar B and row reduce, we can detect contradictions, rows of the form 0, 0, 0 bar C, where C is not 0, which tell us B is not in the column space. This core idea connects to and underpins several important concepts going forward. First, the concept of rank, which measures the true dimensionality of the column space. Second, the Fredholm alternative, a deeper theoretical statement about when solutions exist. And third, the structure of complete solutions, which are built by combining a particular solution with the null space of A. These are the ideas we'll explore next. Here is the one rule to remember. If a combination of the rows of A gives the 0 row, then the same combination applied to the entries of B must also give 0. Specifically, if C1 times row 1 plus C2 times row 2 plus, and so on equals the 0 row, then C1 times B1 plus C2 times B2 plus, and so on, must equal 0. And this is required for solvability. When this condition holds, B lies in the column space of A, and AX equals B has a solution. When it fails, elimination produces a contradiction. 0 equals a non-zero number, and no solution exists. Look at our example. After elimination, the last row of the augmented matrix was 0, 0, 0, 0 on the left side, and B3 minus B1 minus B2 on the right side. For the system to be solvable, that right-hand side must equal 0, giving us the condition B1 plus B2 equals B3. That single test, highlighted in gold, governs solvability for every linear system. This is the solvability test.